Okay, so today we are going to finish up proteins, amino acids, and talk about enzymes. My house should be quiet because my husband just took my son to go get donuts, so hopefully this lecture will not be noisy. I think on the last one you could hear his video game going in the background. So I apologize for that. Hopefully it wasn't too terribly distracting, and if it was, please just ask for clarification on things that you weren't sure about because you were distracted. But hopefully today it'll be not distracting. Okay, so last time I said we were going to talk about the denaturing of proteins starting today. So we talked about the primary, the secondary, the tertiary, and the quaternary structures. Now, when we're talking about the denaturing of a protein, we're talking about the disruption of those stabilizing interactions that we saw. They were the hydrogen bonding, the ionic bonding, the dispersion forces, and the disulfide linkages. Okay, so those were the four that we talked about. So when we see a protein that undergoes the denaturing process, it's the disruption of those, and then the renaturing process is the reconstitution, the rebuilding of those interactions to stabilize the structure. So I know that this is really dark and it's in the crack of the book, so I'm going to tell you what they are off onto the right hand side. So there are different ways that proteins can be denatured, or are denatured, I guess I shouldn't say be denatured, but can undergo the denaturation process. And there are 5 here, okay, and so we're going to talk about those. So the first one is heat. Above 50 degrees Celsius, or exposure to UV radiation. Okay, so when I first started at HBU, my cat was diagnosed with diabetes, and I had to give her insulin shots every day. And I was not familiar with insulin, and that is a human protein. We've seen that here. Remember, the human insulin was our example of primary structure. And one of the things I had to do for her insulin was keep it in the fridge, and that was to prevent the denaturing process as a result of heat. Once it's denatured, the protein isn't active and it won't do its job. So that's why we needed to keep it cool. The second one on here is addition of acids or bases. Okay, and the reason why is if you think about hydrogen bonding, that can ruin hydrogen bonding by allowing acids and bases to be around. It could also potentially ruin your disulfide linkages. Though I think they're a little bit more difficult to break than the hydrogen bonding, because this is a true bond that forms, whereas this is just an interaction. The third one that's on here is the use of organic solvents, and it gives us the example of ethanol or ethyl alcohol. So any sort of solvent that might disrupt the OH bonding that stabilizes it. So same thing as this one up here. So it's really important with these types of things that you keep your, in this case, the syringe that I used for Miss Kitty, I would have to get a new syringe every time, and I gave her insulin twice a day. And so it's just to make sure that you're not exposing not only her to something that's harmful, but the insulin, because once it's contaminated, it can denature and then precipitate out a solution. The fourth one on here is the presence of heavy metal ions such as mercury, silver, and lead. Okay, so if we think about our transition metals, we really need to avoid exposure to silver, mercury, and lead. I'm not sure of the oxidation state specifically, but lead 2+ is a pretty common one. And the reason why is because it can disrupt your disulfide bridges, your ionic bonds, and your hydrogen bonding. Okay, so it can disrupt those three. All right, the fifth one is, it says alkaloid agents or reagents. We need to avoid exposure to those. And it says such as tannic acid used in tanning leather. So anything that is kind of an alkaloid reagent, and then it gives you just the example of tannic acid. Now the other thing that's not on here that usually gets to be, that usually is mentioned, maybe it's not so much true anymore, is mechanical agitation or shaking. So I don't see that on here, though I do remember it's in the old book that it talks about why you shouldn't want to shake your proteins. And so this is also, but it's mechanical. Okay, so maybe these are focusing on chemical. So like with Miss Kitty's insulin, I had to be really careful, and I didn't know it at first, but I would just get the bottle out of the fridge and I'd shake, because that's what I thought I needed to do with liquid medicines. That's what you do with antibiotics. And then she, when I took her back for follow-up, her blood sugars were still really high. And so I had brought the insulin in with me, and they looked at it, and it had precipitated all along the bottom. And they asked me what I was doing, and I told them how I shook it, and they said that, no, you needed to not shake it. So, lesson learned, I had denatured an entire bottle of insulin for my cat, which insurance does not cover. But I learned a lot, and I learned a lot about proteins in that experience, which has helped me with this part of this lesson material. Okay, so the most common ones that you're going to see are the heat exposure, I would say, and the mechanical agitation. The other things I don't think are as common, especially when you're talking about medicines where you're using a new syringe every time. All right, so the next thing that we're going to talk about to end out this chapter is enzymes. And I know that this is so blurry. I'm not sure what was happening with the camera on the iPad. But enzymes are really going to be thought a lot like a catalyst. Okay? And a catalyst is something that will increase the rate of reaction. Okay? So catalysts we use normally in like chemistry, like organic chemistry, general chemistry. We tend to think of them as catalysts. However, when we look at biology and biochemistry, which is what we're in right now, we tend to call them enzymes, even though they kind of operate with the same thing in mind, which is increasing the rate of a reaction. Now, the other rule about a catalyst and an enzyme is that they are not changed. So they remain unchanged by reaction, which really just kind of in the same sense says they are not consumed by the reaction. Meaning that theoretically, we could extract our catalyst or our enzyme and use it again. Okay, so enzymes in the body do the same reaction over and over and over and over again without being changed. Now, there are some examples because enzymes are made up of proteins like lactase, where you have a deficient or a defective enzyme that doesn't do what it's supposed to do, and lactase is an example of that. So the enzyme is a biological catalyst, kind of what we said up here, and the substrate is where or who the enzyme reacts with. So it says a compound on which an enzyme acts. Okay, so we have enzyme and substrate. That is our reactants. Remember back to reactants and products. Now, enzymes are a huge class of proteins. There are so many different examples in your body, and so they do different things. In this case, the book breaks it down into groups of 6, or into a group of 6, okay, kind of like themes. And within that class, there is going to be very different examples throughout the body, but the examples it gives are oxidoreductases. Okay, so this makes me think of redox. So these are things that will do redox reactions. We have transferases. These are things that will transfer something from one thing to another. Hydrolases. These will undergo or will facilitate hydrolysis reactions. Lysases. It's too many S's. I let my southern thing take over. Lyases. These are things that basically, I always think of lysing as cutting, okay? So in this case, that's the best way I can, because it's going to, if I read the definition, it says reactions in which groups are removed without hydrolysis or addition of groups to a double bond. So I like to think of it just in general as cutting, and I think that that's sufficient for what we're looking at. But the important part is it's cutting without water, so it's not like the hydrolases above. Now, isomerases are going to be reactions where the compound itself is converted. So this will to its isomer. So they convert to an isomer. So if you think about the anomers we talked about with carbohydrates, the alpha and the beta, going from alpha to beta, those were isomers or stereoisomers, we said, anomers of each other. So that's an example of something being converted from an alpha to a beta, from a one something to a something else. But structurally, it's going to stay the same. And then the last one is our group called the ligases. Okay. And so these are going to be where new bonds are formed between carbon and something else. Okay, so new bonds centered around carbon and X, which is something else. And the thing that kind of sets this one apart according to this table is that energy is required. Okay, so kind of something that sets it apart. So these are your 6 different classes of enzymes. Within that, there are different examples of proteins that fall into each of these classes. Okay, so let's talk a little bit more about what enzymes do. Okay, so when we're talking about enzymes, there's some important terminology which we're going to see here. The first is the active site, the lock and key model, the induced fit model, and then we'll talk about optimum pH, which is important for our enzymes. So the active site is going to be where the enzyme binds a substrate and where it is transformed to enzyme plus product. Okay. So there's going to be this brief little moment where they're bound together before the substrate is transformed into the product. Okay. So this occurs at the active site. Now, there are going to be 2 models that we use to kind of explain what happens. The first is the lock and key model, which is the model that portrays the enzyme as a conformationally rigid and able to bond only to a substrate or substrates that exactly fit the active site. So the way to think about the lock and key model is your house key, which I know right now you guys might be in a dorm, so maybe the key to your room. So theoretically, your key should only open your doorknob, right? If somebody else had a key to your doorknob, it's not secure. The whole point is that only your key opens that door, except for maybe a master key, but none of your roommates have that same key. Okay, so it only fits to that one site. If you try to put your key in your roommate's dorm and try to open it, it wouldn't work. Even though it may fit, it's not going to actually unlock the door, which is the action that we want. Now, induced fit model is where the enzyme undergoes a conformational change when it binds to the substrate model. Okay, and so this is going to be where the enzyme will basically change its shape in order to induce the reaction it's trying to induce. Okay, so even though it's not directly meant to fit as it is, once it binds, it changes shape, and then it is able to do the reaction. And remember, conformational means changing its shape with respect to 3D. Okay. Now, optimum pH is important because the pH at which an enzyme operates, its maximum activity, is normally a specific range. So if a pH, or if we have something going on in the body, like cancer, something that's systemic, where it's pretty largely found, what it can do is it can throw off the pH in your cells, which then has a trickle-down effect, because proteins and enzymes and things like that, which are sensitive to pH changes, are no longer at their optimum pH. Therefore, they're not able to achieve maximum activity, if any. And so optimum pH is important for optimum reactivity. All right, so what that looks like. So when we have, what's the enzyme and the substrate, you can see the substrate is now in here. The enzyme is still around it. It kind of looks like it surrounds it. And so that's kind of a simplistic form of what it looks like when they bind. Now, we have the lock and key model. So if you see here, this is the key, which is our substrate, the enzyme, which is our lock. The substrate can fit inside the active site, and therefore it unlocks. It makes a complex right there. And then when it unlocks, that is the production of the enzyme plus the product, which is the unlocked lock. Now, induced fit is a little bit different. So we have here, it says right here that it's open. This is our enzyme. Looks like a Pac-Man. And then we see that the glucose comes in here and binds. Upon the binding of glucose, what happens is the enzyme then shuts, okay, producing the enzyme substrate complex. Okay, so this is the conformational change, the opening and the closing. Now, there is another thing about enzymes that's important, which is inhibition, because we're talking about enzymes doing an action. Okay, so inhibition is going to be really anything that tries to prevent that activity from happening. So we're going to have some terminology. Irreversible inhibitor is a substance that inactivates an enzyme by bonding covalently to a specific group at the active site. Okay, so the active site on the enzyme is going to be inactivated, or essentially closed for business. And it's called irreversible, right, because this is not reversible. Now, a reversible inhibitor is a substance that inactivates an enzyme by binding at the active site through non-covalent reversible interactions. Okay, so you can see the terminology. This one said covalent bond, which suggests strength, whereas the reversible used the word interaction, something that's easier to break. Okay. Competitive inhibitors is a compound that resembles a particular substrate and competes with the substrate for binding at the active site of the enzyme, which slows the rate of reaction. So just like if you have a competitor, so like Walgreens and CVS seemingly offer the same groceries, the same products, the same things, however, so we call them competitors, right? Because they're competing for your business. So in this case, you're going to have a compound that is competing with a substrate for the active site on the enzyme. And because it's competing with our substrate, it's going to slow the reaction because of that competition. Okay? And I know this is so blurry, so let me see if I can do a better job of describing what's happening here. So competitive inhibition. See if I can find the figure in my book. Okay, here we go. So we have, in this case, we have succinate, which is here. It's part of our, I think it's a citric acid cycle. It's going to bind to the enzyme, in which produces fumarate, which is another part of our, I'm pretty sure, citric acid cycle. You might see Dr. Morris nodding his head, but I'm pretty sure it's citric acid cycle. And then releases the fumarate. So this is what we want to happen. Okay. However, there is another compound which is kind of very similar, right? So these look similar, and this is malonate, which I'm not sure if malonate is also part of the citric acid cycle or if it comes from another source. I'm not sure of the source, but because it has some structural similarities, mainly the oxygens right here, which you can see that's what's important, it seems to be most important. It's what kind of turns on the enzyme. The malonate can come in and form that same complex, but because it is not the right substrate, no product is formed. So it basically comes in and blocks that enzyme. By blocking the enzyme, it means that our succinate, if I could spell, cannot bind. At least it can't bind until we figure out how to remove the malonate from its active site. Okay, so that's competitive inhibition. All right, non-competitive inhibition, an inhibitor, is a compound that can either combine with the free enzyme or the enzyme substrate complex at a site distinct from the active site, which slows the rate of reaction. So the difference between competitor and non-competitor is that the non-competitive inhibitor binds somewhere other than the active site, whereas the competitive inhibitor binds at the active site. Okay. Feedback inhibition is a normal biochemical process that makes use of non-competitive inhibitors to control some enzymatic activity. So this is like if you have a manufacturing process, right? You're going to start with raw products, you're going to make an intermediate product, then you're going to basically produce it and take it to the stores. Well, you don't want to continue to use your raw product to make more when it's not coming off the store shelves. So normally they'll have a feedback process. People will make small reorders to know that they need products to put on their shelves. So this is a feedback loop, and it basically tells us, do we need to stop the process of the downflow? Okay? So your body does the same thing. There are things that are already in play that should then go back to the beginning of a reactive process and say, okay, we need to stop. We already have too much of the product. Unfortunately, the feedback inhibition can go wrong. Things that are supposed to go back and tell your body to stop making something that it's making, like if you get stung by a bee or bit by an ant or something like that, there's feedback inhibition processes, feedback loops, which will basically go haywire and your body produces a lot of reaction, which is why you swell, turn red, and those things. I'm trying to keep my cat off the tablet. I don't know why cats like computers. All right, enzyme cofactors and vitamins. Okay, so we have a couple more terms to know. So a cofactor is going to be a non-protein component of an enzyme that is necessary for the enzyme's proper functioning. So remember we talked about covalent and co meaning you share something. So in this case, the cofactor is necessary, but it's not a protein. So it's not made up of amino acids, okay? There's all kinds of different cofactors throughout your body that are necessary. A coenzyme is a cofactor that is an organic molecule. So it's a specific type of cofactor. A vitamin is an organic compound that is essential in a very small amount for the maintenance of normal metabolism. And then antioxidants are a substance that prevents oxidation. So you may know of antioxidants when you've heard things about dietary considerations, like this is an antioxidant, like dark chocolate's an antioxidant. You should have these. And then you know vitamins because there's multivitamins, and then there's vitamin C and E. And so some examples of an antioxidant, it would be like vitamin C and E. They can act as antioxidants throughout the body. And so those are some examples of, vitamin C and E. Okay. All right. So there are all kinds of vitamins in the body. We're going to have two different tables, the fat-soluble and then the water-soluble vitamins. So vitamin A, retinol, is physiological function is the formation of vision pigments, differentiation of epithelial cells. If you are deficient in vitamin A, night blindness is is a result, or eventually you would end up with total blindness. Vitamin D increases the body's ability to absorb calcium and phosphorus, which we need for bone health. So you might have heard as a kid that drinking milk will make your bones strong, but it's not necessarily that the milk directly does it. However, the vitamin D in milk will allow the body to readily absorb calcium and phosphorus. If you're deficient, osteomalacia, not sure if I said that right, softening of the bones, which is really known as rickets in children. It's not as common now as it used to be, I think in the industrial times, just because people know now to drink milk more often, or to make sure you're getting vitamin D. In addition to drinking milk, the sun is an important source to activate your vitamin D. So it's a combination of a couple of things. Vitamin E is a fat-soluble antioxidant, and if you're deficient, you can have damage to your cellular membranes. Vitamin K, formation of prothrombin, a key enzyme in the blood clotting process. So if you're deficient, obviously your blood clotting process is not going to work very quickly or work well because enzymes catalyze. And so you'll have an increased time for blood to clot. Okay. Now, when we start talking about water-soluble vitamins, we have a ton of different kinds. You have vitamin B1, B2, B3, B6, B12. Normally, you can buy this as a B complex. Okay. And then you can see that it has coenzyme function, so what it's responsible for, and then you have your deficiencies over here. Biotin, folic acid, pantothenic acid, which is coenzyme A, and then vitamin C, which is ascorbic acid. These are all examples. Okay, so if you ever want to know, I would look at the back of your multivitamin if you take one. If you don't take one, well, I'm not going to lecture that you should, but you should take one. Just to make sure, especially if you're in college, you're probably not eating very well all the time, sleeping very well all the time. I'm not even in college, and I don't eat well and sleep well all the time. And so multivitamin just kind of covers your bases and makes sure that you're getting what you need in order to ensure these physiological processes are occurring as they should. All right, so that should end chapter 14. And this should have been probably about 30 minutes. So that would leave you roughly 20 minutes to ask questions on the homework. As we get closer to the end of the semester, these turn more into conceptual questions, but I do know that you might have some questions about this tertiary identification. So feel free to take the time to ask either Dr. Spencer or Dr. Morris questions. Maybe you're not sure about these enzymes and the competitive inhibition, but please make the most of the time you have with them. And I hope all is going well. Please email me if you need anything. There's 2 more lectures before this last exam, so we're very close to being at the end.